Today we're going to talk about the simple pendulum. So let's draw the diagram first of a simple pendulum. So we have some wall like this with some mass that's hanging like this. So let's call that mass M. And then we have, I'm going to draw a dotted line as the center of the axis. Okay, and then this mass, and then we call the length of this L, or a small symbol like that. And we know that this mg, it has an mg force downward, and it also has a sideways force, mg sine theta. Right? So this is our diagram of a basic pendulum. So now we do analysis on this. Well, first you know that let's say if we have a circle like this, and that we have some arc length, which we call this S, and some radius R, and some angle theta, we know that theta is actually equal to S divided by R. This is just pre-calculus, right? So therefore by this logic, theta times the radius is actually equal to the arc. So in this case, we have a circle as well. So we know that the angular displacement, so let's write that down. Displacement of mass M is actually equal to, well, our angle here is theta as well. Our R in this case is the length of the rope that's tying to the mass, which is length that, right? So this is our X, kind of like the displacement. So now obviously if this is the X, well, what is the V? Well, V is, well, length doesn't change, so it's going to be a derivative of the theta with respect to t. So this is our angular velocity. And then our angular acceleration is obvious as well, as you just take the derivative of the velocity. So this is going to be length times the second derivative of theta over dt squared, right? So let's just keep this in mind for now. Okay, so let's take a look at the force that we have here. Let's draw this diagram right here. So we have a force of mg sine theta. And I'm going to write this mg sine theta as negative mg sine theta because, well, the direction of it is always the opposite direction. So I'm going to give the symbol negative, I'm going to multiply it by -1 so that the direction of it is clear. So negative mg sine theta, we make this equal to ma, right? F equals to ma. So we'll notice that the m cancel out, and we're left with a is equal to negative g sine theta. This is what we're left with, right? And then if we want to, and if you look at this, if you try to plug this in, because essentially what this is the angular acceleration, right? So if you want to try to get that acceleration into our equation, you need to get rid of this length, right? So let's move that into our equation. So this becomes second derivative of theta over dt squared, length divided by length is equal to negative g length times sine theta, and whereas length cancels out. So our differential equation right here is going to be the second derivative of theta with respect to dt squared is equal to negative g over the length times sine theta. This is going to be our differential equation right here. Well, this is problematic because recall that in our previous example, let's say a horizontal string, it has a similar form as this. Remember that for a horizontal string, it was something like d2x dt squared is equal to negative, I think, k over m times x, or something like this, right? But this is problematic because in this case we have a sign right here, but in this case that we doesn't. So how do we get rid of the sign to obtain some kind of similar expression as the horizontal string, so we can have the general solution to the simple harmonic motion in here, right? So how do we get rid of the sign? The sign is problematic. Well, if you know that you can write sine in terms of a power series like this. So sine theta is equal to theta minus theta squared, actually theta cube, right? Like this, and then plus theta to the power of 5 divided by this, right? And then plus blah, 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 blah. And this part is coming from the math department again. I'm not going to go too deep into that, but you can do some research with yourself. So why is this important? Well, this gives us an opportunity so that we can graph it. So we can graph it. So what does the sign look like? So if we have a axis like this, where our y is just the y-axis, our x is, let's say, radian of the theta, then our sign is gonna look like something like this. This actually, I'm gonna draw this with a red line so it's more clear. So it's like this. So y is equal to sine theta, and then our theta is just gonna be a straight line. It's like saying y equals to x, right? Actually, I'm gonna use different pen as well. So it's gonna be something like this. This is y equal to theta. This is very important because, as you can observe here, for the smaller angular diffraction, the second and higher terms are much smaller than the first term. For example, if the theta is equal to 0.1 radian, which is, let's say, a typical value for a pendulum clock, then the second term is only 0.17% of the first term, and the higher term are much smaller still. So it will be something like this. So as you can see, as the value of theta increase in radian, they get off, right? So they're like not matching before. But for this part, where the radian is small, they are identical, right? Because as you increase the value of radium, this and then this will have a big impact on it, and then it will just drift away. But for small radium or small theta, they are actually identical. So the theta is actually equal to sine theta at small theta. Okay, this is only a condition. So this is only approximation for small theta, because as theta get bigger, these two curves are not identical anymore. So it only works if the theta is small. But that's okay, because for a pendulum, the theta, as long as you don't stretch the pendulum or you don't release it at a really high radian, wherever, but it should be fine, right? So the important takeaway here is that for small theta, theta and sine theta are actually identical. So that actually solves our question, because if we move the equation down here, this is going to become second derivative of theta dt squared is equal to negative g divided by length of theta. So here we have successfully obtained an expression that's somewhat similar to the one we have for horizontal spring, and that is actually a very big success. Also, just something to add on for this case, that in this case our omega is going to be square root of g over L. I mean the length. And our period is going to be 2 pi times the square root of L over g. So that's going to be our period, and omega is going to be that. But that's kind of curious and similar, because for this case, our omega is actually square root of k over m. So as you can see, it kind of matches right here. So that's pretty good, right? And then now we can write down our general solution to this simple pendulum. Well, it's going to be like theta is equal to theta, initial theta, which is like the equivalence of an amplitude, is equal to times cos omega t plus phi. This is very similar, because remember, for the horizontal spring situation, the general solution to this is our displacement x is equal to a, which is like the initial amplitude where you released it, times cos theta t plus phi, right? So as you can see, these two are very identical. Our displacement in our angular displacement is actually our starting angular position, which is our, in this case, it's going to be a, but in this case, we have our initial maximum theta, which we call theta 0. And then the rest is just the same. So now we have successfully obtained an expression for a angular displacement of the pendulum. This is pretty important because, as you can see, I wrote my period. My formula for my period is actually t equals to 2 pi times square root of length over g. And this is pretty curious because, as you can see, the period of the pendulum is actually not affected by the initial amplitude where you release it, and that's pretty important because that is why like the pendulum is useful as an accurate timekeeper, right? When you see a pendulum at your home, it doesn't go from a really big amplitude. It's always like a small amplitude, because when it goes really big amplitude, all of these equation doesn't work, because our series or our period of sine theta is equal to theta just collapse when the angular is really big. But for small amplitude, our the period of our pendulum is independent of our amplitude of where we started. So that's pretty good, because we want the period to rely only on the length and the gravitational constant on Earth. So in that case, our period is always a good timekeeper, as you say. So yeah, so another curious fact is that if we define our length to be 1 meter and our g to be 9.87, then the period of a simple pendulum is like, if you just plug those two values in, which is t equal to 2 pi times, let's say length is 1, this is 9.87, right? This is actually equal to 2 seconds. This is pretty interesting because this is actually originally defined as equal to 1/2, like a second. Remember, like back in like the, let's say 1800s or 1700s, I'm not sure about the time. How they define 1 second is that it's actually defined as equal to 1/2 the period of a 1 meter simple pendulum. Remember, our length here is 1 meter. So that's pretty curious, is that they define the second, the idea of a second, as like the half period of a 1 meter pendulum, right? So this will all be our simple harmonic or our displacement equation for a pendulum.